Welcome back to OCR MEI Further Mathematics past paper walkthrough. Today we're doing section B of the 2014 C3 paper. So yeah, basically just let's get started.
So question 8 part 1, show algebraically that f(x) is an odd function. That is quite straightforward. So the way to show whether a function is odd or even is to show that if y of f minus x is equal to f of x, that would be even. If it's equal to minus f of x, then this is odd. So let's have a try, shall we? So fx, from the definition of the question, is x on root 2, 2 plus x squared. So we've got this sorted. Now we need to fit in a negative x in the function, which gives me f of minus x is equal to minus x over the square root of 2 plus minus x all squared, which gives me just minus x on square root of 2 plus x squared. Now this whole portion on the right is just fx, therefore it's minus f of x, and so we've proven that this function is odd. Now for part 2, it's given that, well, we need to show that the derivative of fx is 2 on 2 plus x squared all to the 3/2. So let's have a try. Let's see. So it's just simple differentiation. So we have x on root 2 plus x squared, and it's better to write this whole thing in index form into x 2 plus x squared all to the minus a half. So square root is a half and 1 over is negative. So we've got this. Now we want to do the derivative. So f of x, f prime x is, we can use chain rule. So the first chain would just be differentiate the x and leave the bracket b. So we have 2 plus x squared to the minus a half. That is the first part. Then we add the second half of the chain rule. So we have the x being intact, then we multiply by the derivative of that bracket, which is minus a half 2 plus x squared, and that would be to the power minus 3/2, and that we have to chain the derivative of the middle, which is just a 2x. So multiply by a 2x, and with this whole thing we can cancel a few things out, and we should be left with 2 plus x squared to the minus a half minus x squared 2 plus x squared minus 3 on 2. So we've got that set, Now, because the format that the question shown is in kind of just simple fraction form, so we need to, well, merge these two units together into one fraction. So for the first part on the left, we basically can multiply the top and bottom of the fraction by 2 plus x to the 2 plus x squared, all to the power of -1, which would give us so 2 plus x squared to the 3 on 2, and the top would just be 2 plus x squared. And for the other counterpart, we just have a minus x squared, which means that these two x squares can be cancelled, and we're left with 2 on 2 plus x squared, 3 on 2, which is what the question gave us from the first place. So hence, find the exact gradient of the curve at the origin. The origin is 0, 0, which means that x has to be 0. So this term goes, and we're left with 2 on 2 root cubed. And that whole thing, so we know that root 2 squared is just 2, and so the root 2 squared can cancel with the 2 to give just 1 on root 2. So that would be the exact gradient at the origin. Now next we have the third part, which is find the exact area of the region bounded by the curve. So let's have a go. So area, so we have the region from x is 0, well, y is 0, to x is 1. So basically, in terms of the logistic of the question, we can disregard the negative domain and range. So we just have something along the lines of this curve, and we want to cut off at x is 1. So basically we want the entire area under the curve here. So this wedge is what we want, and we know the equation of the curve. We know that we can do an integration from the origin to 1 by dx. So let's have a try. So we basically want to integrate by dx of fx, and the boundary limit would be 1 to 0, and we know that fx is given by the question, so it's just x on root 2 plus x squared, and that whole thing can be integrated. And now this is the more tricky part, is how do you do this integration? And the solution would be just integration by substitution. So u is 2 plus x squared, and so du by dx is just 2x, and this x could eventually cancel with that x, so that is fine. And now we have integrate 1 to 0 x on root u dx, which is du on 2x, and goodbye x, and we're left with integral of, well, the limits have changed actually, so this is wrong. Let's just not think about the limits for now, because we can get away with not changing the limits if we resubstitute the u by the end of our numerical calculations. So we have u to the minus a half du. That is a simple integration, which gives me u to the a half times 2. So this whole thing, I need to put in the boundaries, and that before I put in boundaries, I substitute in the formula of u, which is 2 plus x squared. And now I can just use the original limits, so that saves you a bit of calculation. So with that information, we can now do the substitution. So if x is 1, then we have 2 times 3 to the power half minus 2 times 2 to the half, which is let's see, right, this is what happens if you don't pay attention. So we have a half in front, and so we have a factor of half in front of the whole thing as well. So basically this 2 cancel with the 2's in the fraction, and you're left with root 3 take root 2, which yes, in fact for this part of the question you need the exact area, so do not use your calculator, but I don't see why you would. Once you've got this part, you should get all the marks. Yes, so part 4 now, we can have a look. So part 4a, show that if y is that equation, then, well, basically it's a rearrangement, isn't it? So let's have a go. Let's see. So y is x on root 2 plus x squared, and I know that I can multiply both sides by, actually we can just square both sides, that would work out a bit easier. X squared on 2 plus x squared. Now multiply both sides by the denominator, you get 2y squared plus y squared x squared equals x squared. And now we want to recollect the x term, so we no, actually we can factorize out the y term, and we get, oh no, actually this is breaking open the bracket is a big mistake. So yeah, let's do it step by step. So we went from this down to here. Now we can divide both sides by y squared x squared to get 2 plus x squared on x squared is just 1 on y squared, and on the left we have 2 on x squared plus 1 is 1 on y squared, which is what they want. So yeah, sometimes you can tunnel vision and do a lot of unnecessary algebra, but just if it's not working out, then just kind of step back and rethink what you're doing. Now, differentiate implicitly to show that dy by dx is 2y cubed on x cubed. So let's have a look. So differentiate this implicitly would mean that I am differentiating 1 on x squared by dx, which should give me, well, let's put it in index form first, which is 2x to the minus 2 plus 1 is equal to y to the minus 2, and differentiate both sides implicitly. I know that minus 4x to the minus 3 dx, well, actually, for A-level implicit differentiation, you don't need the dx bit. On the 1, we just differentiate to 0, and y, we have minus 2 y to minus 3 dy by dx, and now we have this equates to minus 4 is minus 2 y cubed x cubed, and this, if we rearrange for dy by dx, we have dy by dx is minus 4 on 2, well, minus 4 on minus 2 is just plus 2, then y cubed on top, x cubed on the bottom. So yeah, that is the expression given, and we need to explain why this expression cannot be used to find the gradient of the curve, and that is because the gradient of the curve at the origin, we need to divide by 0, and divide by 0 is not allowed. So that's basically what we want to say. And yeah, so that's question 8. Okay, question 9 is more equations on curves, so it's more integration, and also we have variables that we need to take care of. Y equals to mx. Let's see, show that the x-coordinate of P, the point P, is minus a half natural log of m. So to find P, we just find the equation where the two lines intersect, or the simultaneous solution of the two equations, which is mx equal to xe to minus 2x, which means that you either have x as 0, or you have m equals to e to the minus 2x, and clearly p doesn't lie on the origin or the 0 of x. So we can now natural log of m is just minus 2x, and therefore x has to be minus 1 on 2 ln m, which is what we were given. So that is an easy 3 marks in the pocket. Part 2, find in terms of m the gradient of the tangent to the curve at P. So we want to differentiate, so dy by dx is, we need to use chain rule, product rule, that is, not chain rule. Yeah, so e to the minus 2x plus x times minus 2 e to the minus 2x, and that would give me x 1 minus 2x e to the minus 2x. So we have this information, but we want to express it in terms of x, which means that we substitute the, we want to express it in terms of m. I can't speak today, can I? So substitute using this equation, we get that we have 1 plus natural log of m. Let's see, that is true, and we have e to the, so minus 2x is just ln m, because e to the natural log is just cancel out, we get m, so we have m 1 plus ln m as our solution. So now we have part 3, which is show that m is e to the minus 2 and find the exact coordinates of P. Let's see, so I know that dy by dx is this. Let's see, how can I do this? Oh yeah, right. So I know that the on y is mx, we know that the gradient has to be minus m in this situation, because OP and the tangent is equally inclined to the x-axis, and that means that for a curve or for two lines with equal inclinity or inclination, we can say that this theta is equal to that theta, which means that the gradient, if dy by dx is positive on the top, then it would be negative on the bottom, which means that the gradient dy by dx is minus m. And with that said, we can now do some algebra. Oops. And we can, let's see, so let's first open this up, equals to m plus m ln m, and this we can add m to 2m plus m ln m is 0, and I can factorize out, and this is an unnecessary step, isn't it? But then we know that m can be 0 or 2 plus ln m can be 0. We know that this is absolutely nonsense, so we can disregard, and we have ln m is minus 2, and therefore m is e to the minus 2, which is the solution given. Now we have the last part of this question. Find the exact area of the region shaded between OP and the curve. Now we need to take out the equations that we've found. So the first useful equation is this one, x is minus a half ln m. The second useful equation is m is e to minus 2. And so we know that for point P, x is minus a half. Natural log of e to the minus 2 is just minus 2, which means that we have px is 1. So that's the important bit that we've collected, which means that we now only need to care about integrating the equations between those to that point and origin. So we now know the integration boundaries, and we know that the region between is just the upper curve subtract by the lower curve, which is x e to the minus 2x subtract by mx. And again, from previous, we know that m is e to the minus 2. So we have x times e to minus 2x minus e to minus 2. And this would be used to be integrated. So we have x e to the minus 2x take e to the minus 2 dx, and I think it is smooth sail from here. So let's see. So integrate, so because this is another product, we need to use the integration by parts method. So let u be x and v prime be e to the minus 2x. Well, take e to the minus 2. We know that u prime has to be 1 that way, and v has to be the integral of these two, which is minus a half e to the minus 2x take x e to the minus 2, because e to the minus 2 is just a number. And now we can just use by parts uv, which is x times minus a half e to the minus 2x take x e to minus 2, 1, 0, subtract by the integral, which is basically just u prime v, which is just v, minus a half e to the minus 2x take x e to the minus 2 dx. And for the left part, we have, for x is 1, this is 1, so minus a half e to the minus 2 take e to the minus 2, and the lower limit is just 0 times that is 0, 0 times e to the minus 2 is 0, so that's straightforward. Now we factorize out the minus a half. Actually, that's a bad idea. Yeah, let's just integrate as is, and we should get, because now it's a simple integration for both of them. We have minus plus a quarter e to the minus 2x and take away x squared on 2e to the minus 2. So it's always good to do sanity checks. So if you differentiate this expression, you should get that expression, and if you differentiate this, you should get that. Yeah, so that looks okay, and we put in the limits 1 and 0, and we should get, well, on the left here we have minus 3 halves e to the minus 2, then we take away, for x is 1, we have a quarter e to the minus 2, take a half e to the minus 2, then 0, this second term goes away, the first term is e to the 0 is plus a quarter, but bear in mind we're subtracting actually, so just bear that in mind, because this is the lower limit, we subtract. And let's see, so now we have minus 3 halves, then minus, for this bit it is a quarter, take a half, that gives me minus a quarter, so minus a quarter and negative is plus a quarter. So we have 6 on 4, e to the minus 2 plus a quarter e to the minus 2, and that adds a quarter, which would give me 1/4 take 5/4 e to the minus 2 as my final solution, and this is the exact region. Yeah, that would conclude this second part, section B of the paper, and I find this paper rather, well, straightforward, maybe except for the fact that some of the algebra manipulation could be tricky, and also for section A, question 7 is like, it's a you either know or don't situation, which is not that nice in terms of questions. However, most of the paper involves simple calculus, and if you've practiced enough calculus, you should be able to do them all without problem. And with that said, I hope you have a good exam, and I will see you next time.